Hello students, in this video we'll see how to relate Christoffel symbols to derivatives of the metric tensor in certain coordinates. Let's be given coordinates x1 through xn. This time we won't make any coordinate changes, we're just going to fix these coordinates and look at the metric tensor. Then consider EI, which is dr, the vector field position on Euclidean space with respect to the xi coordinate, xi like this, okay? And then form the metric tensor and form the metric tensor. Gij, the Riemannian metric tensor, Gij, which is just EI dot EJ, okay? Excellent. That's a two covariant tensor over there, Gij. And so now, of course, we want to try to relate this to the Christoffel symbols, right? So what are the Christoffel symbols? So recall that if I look at the derivative of this, so if I look at dEI dxj, this is going to be gamma of ijk ek, because ek is a basis over here. So these define the Christoffel symbols, gamma ik, Christoffel. And we proved in a further video that previous video that there's an intrinsic form of these Christoffel symbols, right? And so the intrinsic form is the following. It says that gamma of ijk can be expressed in terms of derivatives of these metric coefficients, right? So this is going to be 1/2 glk. That's the inverse of this metric tensor, right? And then we're going to have a partial gi, gil, partial xj, plus partial gjl, partial xi, and then minus partial gij, partial xl, okay? And so this gives me the Christoffel symbols. Now these are the Christoffel, these things don't behave as a tensor. We're seeing in the further video that these things do not transform like a tensor. You might say, oh, look, this is going to be a 2 covariant, 1 contravariant. Not true. These things are not tensors, so let's make a note of that actually. This is not a tensor. But it's going to help us build a tensor called the covariant derivative. That thing itself is not a tensor, so these Christoffels are not tensors. That's very important, not a tensor. Even though they look like them, not tensors. Okay? And so there's also a way of lowering the index over here. And so there's a different, these are called Christoffel symbols of the second kind. The Christoffel symbols of the first kind, if and only if we get these new things over here, is call them gamma and then k, comma, I, j. And that's just what we get if we don't have this symbol over here, right? So in other words, if it's between 1/2 dg, ik, xj, plus dgjk, xi, minus dgij, dxk. Those are Christoffel symbols of the first kind, okay? And so now what I want to do is I want to do a symmetry trick over here. I'm going to take these equations over here, and then I'm going to interchange the k and the I, right? So I'm going to look at gamma of I, comma, kj. So let's do it slowly and see what we get. So everywhere there's a k, I'm going to replace with an I. So this is going to be a partial g. Now my I is k and my k is I, so this is going to be the same thing actually, just ik with respect to xj, because remember the metric is symmetric. It doesn't matter if I do I first, j first, because it's a dot product and it's symmetric, plus dg, and then my j is really what? My j is still j, but my k is now I, so that's going to be a jij, and my I is now k, xk. And then minus what? Minus partial g, and then my I is what? My I is now k, and my j is still j, over partial xi, like that. Okay, excellent. And so now, if I add these equations together, what are we going to get? So let's add these equations together. And what's going to happen over here? So look, we have a gik, and then look at these things over here. That I have a gij with a positive, gij with a minus, and then gjk with a negative, gjk with a positive. So those other terms cancel out. So we've just proven that gkij plus gamma ikj is equal to what? Is equal to partial g I k partial x j. So this is one really important relationship because we're going to use this together with a relationship for the derivative of the metric tensor, right? So now, of course, what does this GLK mean? This GLK means exactly what? So now notice that this thing comes up a lot. And so I can say that G, let's say JK, and then G lower KI is equal to delta, of ij, right? And they're inverses of each other, right? So let's take this inverse relationship over here and differentiate with respect to xl, for example, right? So that would say that partial g jk with respect to xl, gki plus gjk, gjk, and then partial g, is ik, just to keep lexicographical order and preserved, is equal to 0, right? By differentiating this relationship with respect to xl, like that, okay? And so now I'm going to contract this thing over here. And so what I'm going to do is I'm going to contract this with a g, what do we want to do over here? I'm going to take the I and turn it into a, let's see, what do we want to do? So I have a k and a j. That's good. And so I'm going to hit this with a g. I'll hit this one upper. All right, good. And so I want to hit this with a gm, and then we can get rid of the k over here. Do I have any mistakes in my notation? Should be no mistakes. It's an I, good. Okay, and so let's do a contraction. Take this whole thing over here and contract it with g and then mk, for example. Let's see what we get when we can do this. Well, if I do gmk with this thing over here, that's going to give me a delta im, delta mi. All right. And we don't have an mi, so we might need to change this to a, probably a, I want to sum over delta I. So let's change this k over here to an I, so my mistake. Let's change it a little bit. So I'm going to do a g, and then I want to get rid of that k over there, so I'm going to do a, I'm going to do a gim, like that. Great. And so now if I do this, what does it become? Now this becomes a delta what? This becomes a delta mk, partial g, j, k, partial xl, and then plus a gim, g, j, k, partial g, I, k, partial xl is equal to 0. Okay, excellent. And so now what this allows me to do is this allows me to say that this thing over here, so now we can conclude that that a partial g, now my k turns into an m, so this is a partial g, j, m, partial xl, is equal to what? Is equal to negative gim, g, j, k, and then a partial g, I, k, partial xl, okay? And so now this tells me that partial g, j, m, partial xl is equal to, now I'm going to write one more step, gim, and then g, j, k, and I'm going to fill in this relationship now over here. This is going to be a, so I have a, and then my only thing that's going to change is my j's are going to turn into l's, right? So it's going to be a gamma of k, and then what? Gamma of kil, and then a plus gamma of what? Plus gamma of ikl, like so, okay? Good. And so now what is this first thing over here? This first thing over here, I have a g, so I'm summing over what? I'm summing over I, I'm summing over, so whenever I sum over what? Whenever we sum over that top index over here, okay, what's the relationship between these things over here? So the relationship is that if I look at this lower index over here, this gjk, and hey, with gkl, that means I'm going to raise this l to the top over here, right? So I'm raising the l to the top. So in other words, I have to sum over, the index has to be in the first slot over here. So I have this gjk over here, right? That's going to hit this thing and raise this to a negative gim, and then gamma upper what? Gamma upper j, IL, right? Now I'm summing over L. Remember, I'm summing over I over here, so I have a J and an M on top and an L on the bottom, which works out perfectly. And then I have a minus GJK, and now I'm going to sum over I over here, so I'm going to bring the M upstairs. So it's going to be a gamma of M and then KL like this. I sum over K, I have a J and an M on top, I have an L on the bottom, so I have this beautiful relationship that the derivative of these inverse of the metric tensor, GJM, with respect to XL, can be written in terms of these upper tensors, in terms of these Christoffel symbols over here. And this relationship would be very, very important for us who are doing change of coordinates with respect to the metric tensor and trying to figure out tensorial relationships that are satisfied by the covariant derivative. So this sort of a calculation right here may seem like it's just a lot of index juggling and a lot of contractions and a lot of raising and lowering, but it's a very important technique in order to figure out how the metric tensor changes with respect to different coordinate systems and how the derivatives of the metric tensor change, and it allows me to get transformation laws for the Christoffel symbols, which would be an essential tool in computing covariance, divergence, Laplacian, and curl, and these more general coordinate frames. Thank you very much.